my friends, now that we have finished discussing the different structures that form in a rock in the primary stages or as a result of applied directed stress or by deformation. Now, before we go into the detailed discussion of how the behavior of materials change with the change in several factors, let us briefly consider the situation that we have discussed earlier while discussing the various deformation structures. In contrast to the stress ellipsoid, where the length of the principal axis are related to the magnitude of the principal stress acting along them, in stress ellipsoids the physical length gives the shape or defines the shape. Thus, in case of if we try to compare the stress ellipsoid of a stressed body, of a deformed body, the stress with the strain ellipsoid, the stress ellipsoid will have the greatest principal axis parallel to the direction of maximum compression, because that is the direction in which the magnitude is greatest, while in case of the strain ellipsoid the corresponding axis, principal axis, will be the shortest one. Though this type of comparison is not mathematically or scientifically correct, because one is an imaginary figure and the other is a physically existing figure. An idea about the stress ellipsoid and the strain ellipsoid can be had from this comparison. In case of the strain ellipsoid, the three principal axes are termed the greatest, the intermediate and the least or shortest principal stress axis. The greatest being represented by lambda 1 as represented by the quadratic elongation along it, the intermediate by lambda 2 and the least principal strain axis of the ellipsoid by lambda 3. Strains may be of different kinds. If lambda 1 is much greater than 1, which is the radius of the original sphere, and lambda 2 and lambda 3 are both less than 1, that is, there is extension in one direction and shortening in the other two, the type of strain is known as constrictional type. While if lambda 1 and lambda 2 are both greater than 1, that is, there is extension in two directions and lambda 3 is shorter than 1, the type of general strain is known as flattening. At this point of time, it should be remembered that we are considering here only constant volume strain or constant volume deformation, because if we try to accommodate volume changes, the mathematical and conceptual aspects become very complicated. Deformations may be such where lambda 1, lambda 2 and lambda 3 are all unequal, but lambda 2 remains equal to 1 or the diameter of the original sphere. There is extension along lambda 1 and shortening along lambda 3, but no deformation along lambda 2. The type of deformation is known as plane strain. When in the constrictional type of strain there is extension along lambda 1 and equal shortening along lambda 2 and lambda 3, resulting in a circular cross section of the ellipsoid perpendicular to lambda 1. This is called as uniaxial extension, and the strain ellipsoid is known as a prolate strain ellipsoid, loosely called the cigar shaped strain ellipsoid. In flattening type, where there is extension along lambda 1 and lambda 2, if there is identical extension along lambda 1 and lambda 2 and shortening along lambda 3, then the cross section of the ellipsoid perpendicular to lambda 3 will be circular and whose diameter is greater than 1. This type of deformation is known as uniaxial flattening. The ellipsoid is called an oblate ellipsoid and loosely or generally called the pancake type of strain ellipsoid. So, we can see that there are 5 possible types of strain ellipsoid possible. One where there is extension along one direction and equal shortening along the other two, uniaxial extension. One where equal extension along two directions and shortening along the third, uniaxial flattening. There is general constriction, general flattening and plane strain. Several structural geologists have started to work on the mathematical representation of the different types of strain, and these can be seen in the works of Flynn, who has drawn a diagram representing these 5 types of strain. While on the subject of strain ellipsoid, let us try to look at the progressive deformation during a deformational phase. What happens is that at every point of time during a phase of deformation, continuous phase of deformation, new strains are added to the already strained body. During deformation, there may be 2 types of strain. One we call the coaxial strain, means that the orientation of the principal axis remain the same throughout the deformation history, and one we call the non-coaxial strain, is where the orientation of the 3 principal axes of strain change during the deformation phase. Without going into the 3-dimensional aspect of it, let us take up the concept of coaxial and non-coaxial strain in 2 dimension. Let us consider a circle. If we superimpose the ellipse on the circle, there will be 2 lines which have not changed their length, where the ellipse and the circles intersect. These lines which have not changed their length during the deformation are known as lines of no finite longitudinal strain. These 2 lines separate the ellipse into 4 zones, 2 of which are zones of extension and 2 of which are zones of shortening. That is, the lines in the zones of extension have been elongated from their original length, and lines in the zone of shortening have shortened from their original length. In case of non-coaxial strain, where the principal axes change their orientation, the lines of no finite longitudinal strain also change their orientation, thus adding more zones to the deformed strain ellipse. At any stage of deformation, if we draw the lines of no finite longitudinal strains for the previous stage and the next stage, there may be zones where the lines go on extending, there may be zones where the lines go on getting shortened, and there would be zones where the originally extended lines are getting shortened and the originally shortened lines are getting extended in the next stage of deformation. These changes in the deformation history during a non-coaxial progressive deformation results in the development of complicated structures. For example, the lines that lie in the zone of shortening and goes on remaining in the zones of shortening will produce folds. The lines that remain in the zone of extension will go on producing boudinage. But the lines in case of a non-coaxial progressive deformation that move from zones of shortening to zones of extension will show first folds, then boudinage, and lines that move from zones of extension to zones of shortening will show first boudinage, then folds. This will explain how rocks we find only folds along certain zones, only boudinage along certain zones, folded boudinage in certain areas and boudinaged fold in certain areas. This is a result of non-coaxial progressive deformation. By the way, strain can also be represented in 2 dimension by 2 simple parameters. When a square is deformed into a rhombohedron, that means that during this homogeneous strain the straight lines remain straight, but they change in angle. This type of deformation is known as simple shear. While if a square is deformed into a rectangle, then the principal axis, for example the north south and east west lines, mutually perpendicular lines, they will retain their orientation, but all other lines, especially the diagonals of the square, they will change their angles as the square is deformed into a rectangle. This type of deformation is known as pure shear. The simple shear and pure shear are the types of strain reflected in rocks. The pure shear produces the foliations and lineations, where the foliations develop parallel to the lambda 1 and lambda 2 plane perpendicular to lambda 3, and in simple shear the fracture planes cause the folding of the planes by shearing along the fracture plane. So, now we have a idea about the stress and strain that are responsible for the development of folds and faults and joints in rocks. In our next episode, we shall be discussing how the deformation in rocks is controlled or governed by the physical parameters like temperature, pressure, time and presence of fluids.